Hi everyone. So we're going to pick up with the last two lessons here in your notes. They're very quick, and then we're going to go over the FRQs that you did last night for homework. So let's take a look at what we have here. So yesterday we were talking about the common ion effect and how adding an ion can shift the equilibrium of my system and cause my substance to become either more soluble or less soluble, okay, meaning that more of it will dissolve or less of it will dissolve. Well, the same thing happens when I change the pH of my solution. So the pH is a measure of the acidity of a solution. We're going to talk a lot more about this in the next unit. But the pH is equal to the negative log of the concentration of H3O+, and that's how we calculate the actual pH of my substance. Substances that are acidic tend to have really low pHs, less than 7, and those that are basic tend to have high pHs that are more than 7. So if a substance has a basic anion, meaning that it's an anion of a weak acid, or it's something that's going to form a strong base when I have it in solution, it will be more soluble in an acidic solution. The solubility of a compound containing this basic anion increases as the solution becomes more acidic, meaning as the pH decreases or the concentration of H3O plus increases. What does this mean? Well, we know what usually makes a base are these hydroxide ions, these OH minus ions that we see right here. Okay, I can also have a strong base like this F minus ion. This would be considered a pretty strong base here. Its conjugate acid would be HF, which is a weak acid. That makes this a strong base. These substances are going to react very strongly with H plus ions or these H3O plus ions. Really, when we say H plus ions and we say H3O plus ions, it's basically the same thing, because if we have free H plus ions in solution, they're always going to react with water to form this H3O plus. So if I have H plus ions, they'll react with OH minus ions to form water. And that'll pull this OH minus ion out of our solution. When we decrease that concentration of OH minus, well, that's going to shift my reaction to favor that decrease, the side where that decreases, and I'll end up having more aqueous ions here. Same thing would happen with F minus ions in our solution. If we add a compound that releases these H plus ions, so if we add something that's acidic and we release H plus ions into solution, these F minus ions will react with the H plus ions, okay, and that'll be pulled out of solution here, meaning we'll decrease the concentration of F minus. So if we look at a practice question with this, this says that calcium hydroxide and lead chloride both have limited solubility in neutral water. When acid is added, the solubility of calcium hydroxide goes way up, but that of lead chloride doesn't change. Which statement best explains the acid impact? So if we look at this, the calcium hydroxide is in equilibrium with these aqueous ions, Ca2 plus, and my two OH minuses here. If I add an acid, well, that acid is going to release H plus ions. That's what an acid does in solution. Those H plus ions are going to react with this OH minus ion here to make water, and that's going to pull OH minus out of the solution. That means that the concentration of these free OH minus ions is going to decrease. This reaction will shift towards that decrease, which means I'll have less of my solid and more of these aqueous ions. That means its solubility, or how much of the ions can dissolve, will increase. But if I look at PbCl2, there's no H plus here. There's nothing here that H plus will react with in a strong way. I don't have a strong base. I don't have these OH minus ions. So it won't have the same effect on this PbCl2. So my answer choice that says that should be answer choice C. Answer choice C says that the acid reacts with the hydroxide that is produced from calcium hydroxide. So C should be my answer here. Take a second and try question 2. Okay, so when looking here at question 2, it says, would the molar solubility of CrOH3 increase or decrease as the pH is lowered? What we want to note here is that when we say the pH is lowered, that means it's becoming more acidic. And if it's becoming more acidic, that means H plus ions are being added to the solution. So let's write out the reaction here for what this would look like. Okay, so we have our CrOH3 in equilibrium with its aqueous ions, Cr3+, and OH-. So if this is becoming more acidic and we're adding H+ ions, these OH- ions are going to react with those H+ ions. That's going to pull these out of solution. So my concentration of OH- will be decreasing here. That means that my reaction is going to shift to favor the production of these products here because I'm losing this concentration of OH-. I'm decreasing it. So if we shift to favor production of the products, we'll have more ions in solution and less of the solid, so the molar solubility should increase here. That molar solubility should increase. Okay. Last part of the unit that we need to look at very quickly is the free energy of dissolution. What we mean when we say free energy is the Gibbs free energy. The Gibbs free energy really decides whether a reaction is thermodynamically favorable or unfavorable. If a reaction is thermodynamically favorable, it will happen. It'll proceed spontaneously. If a reaction is thermodynamically unfavorable, that reaction won't happen. We would have to change the conditions to make that reaction happen. This Gibbs free energy is related to the enthalpy, which is the delta H, which we spent a lot of time last unit talking about, and the change in entropy, which is this delta S. Remember that entropy is a measure of the randomness of my system. And this is at a very specific temperature. And I have an equation that shows me how I can relate these variables together. And this equation is on our reference table. And in Unit 9, we're going to learn how we really use this equation. But the delta G is the change in the Gibbs free energy. It's equal to the delta H, or the change in enthalpy, minus T, which is the temperature, times the delta S, which is the change in entropy. Systems in nature tend to favor reactions that are exothermic with a negative delta H, because in order for a reaction to be considered thermodynamically favorable, that delta G should be negative. So if delta H is negative, well, that is most of the time going to show me a negative delta G here. But with that negative delta H, I also should have an increase in my entropy, meaning that delta S should be a positive value. Because if I'm taking a negative delta H and subtracting a positive value from it, that's always going to give me a negative delta G here, which will be a favorable reaction. But there are systems that are not favorable that can become favorable at specific temperatures. So if delta G is negative, the system is said to be thermodynamically favorable, and the reaction will occur spontaneously. If it's positive, system's not thermodynamically favorable, and that reaction will not occur at that temperature. And if delta G is 0, that system is said to be at equilibrium. So there's a reaction happening in the forward direction and reverse direction, but those rates are equal, so the Gibbs free energy is equal. The free energy change for dissolution, it reflects a number of factors here. The breaking of those intermolecular attractions that hold a solid salt together, the reorganization of the solvent around the dissolved species, usually water, breaking those hydrogen bonding forces of attraction between water so they can surround the solvent, and the interaction of the dissolved species with the solvent. Generally, we're talking about an ion dipole force of attraction there. It is possible to estimate the sign and relative magnitude of the enthalpy and entropy in each of those situations, and that can really give us a good hint as to whether the system is going to be considered thermodynamically favorable or thermodynamically unfavorable. So we're going to be talking about this chart a lot more in Unit 9. Really what we need to know right now is that if delta G is negative, that's favorable, and that will be spontaneous at that temperature. If the delta G is positive, that's not a favorable reaction. That won't happen at that given temperature. And if it's a question mark, that's what we'll learn to determine in Unit 9. That part not really going to be on the test so much. What's more important here are our actual solubility and equilibrium questions, like we were doing in last night's homework. So let's look at these homework problems and go over them together. Okay, so here in this first problem, they wanted me to write the expression for Kp here. So I need to remember when I'm writing a Kp expression that I'm only including my gases here for pressure. So my Kp for this reaction, again, P stands for pressure. My K values are always going to be my products over reactants raised to their stoichiometric coefficients, but I'm not going to include this NH4HS here because it's a solid. So my Kp would be the pressure of NH3, or the partial pressure of NH3, times the partial pressure of H2S. Both have a stoichiometric coefficient of 1, so they're both raised to the first power. Okay, and then it says to calculate the numerical value of this at 25 degrees Celsius. So it says that the pressure inside the reaction vessel is found to be this point. Oh, I just crossed it out instead of underlining it. Sorry about that. This 0.659 atmospheres here. That's the total pressure inside the reaction vessel at equilibrium. We know that this pressure is caused by the gases only here. And since they both have a stoichiometric coefficient of 1, if I were to look at this in a Rice table, they're both starting at a pressure of 0. They're both changing by a factor of x, which means that at equilibrium, they both have a pressure of x here, which means that their pressures are equal. And if I remember Dalton's law of partial pressures here, I know that the total pressure in a mixture is equal to the sum of the individual pressures. So that would be the pressure of NH3 plus the pressure of H2S. I know that the total pressure is 0.659 atmospheres. I know that the pressure of NH3 at equilibrium will be X, and I know that the pressure of H2S at equilibrium will be X. So I've got 0.659 equals X plus X. I'll solve for my X value here, and that should come out to 0.3295. And that's going to be the pressure of each species at equilibrium. So if I plug this into my Kp expression, my pressure of NH3 is 0.3295, and my pressure of H2S is 0.3295. Multiply those together to get my Kp value, and that should give me 0.109. Remember, these K values are unitless, so I don't include a unit here. Looking at this next problem here, okay, it wants me to calculate that new pressure once equilibrium has been reestablished here. So equilibrium had to be reestablished because some extra NH3 was added into this system. And after that addition, we found that the pressure of NH3 was twice that of H2S. So back in that Rice table, instead of that pressure of NH3 at equilibrium being X, well, now it's going to be 2 times X. We know that the value of Kp does not change when I'm changing anything else here. The only thing that changes the value of K is a change in temperature. And I'm not changing my temperature here. So I know that that Kp is still going to be what we calculated in the last problem. That Kp is still going to be equal to 0.109. What is changing is how what I have each pressure being here. So I know that for my H2S, hey, the pressure is still X, but for my NH3, the pressure is now 2X. It's double what the pressure is for H2S, because that's what it says in the problem here. Okay? So I can combine my like terms and solve for my X here. Okay, and we should come up with my X being 0.233, which tells me that the pressure of NH3, which was equal to 2 times X, would be 0.467, because that was a 0.233 repeating, and the pressure of H2S would be equal to 0.233. Almost forgot my units here. Please don't do that. But that would be my final answer here. Okay, then in looking at question C, question C says in a different experiment, NH3 gas and H2S gas are introduced into an empty 1-liter vessel at 25 degrees Celsius. The initial partial pressure of each gas is 0.5 atmospheres. Calculate the number of moles of solid NH4HS that is present when equilibrium is established. And it gives me an R value here. The fact that this gives me an R value gives me a hint that I'm probably doing my PV equals nRT at some point in this reaction. Okay, so what I need to figure out are the pressures of these gases that actually reacted. And I can look at a little simple stoichiometry here to figure out how many moles of my solid that would mean reacted. And I can figure out how many moles of solid are left or are present at equilibrium. Okay, so what I want to do here, I want to look back at that number that I had in part A, okay, where I saw that my equilibrium pressures of each of these substances was 0.329 or 0.33 atmospheres here. So at equilibrium, again, the pressure of H2S was 0.33 atmospheres, and the pressure of NH3 was 0.33 atmospheres. Okay, so if I insert these numbers into a Rice table for this reaction, so I know that my reaction I have up here, got this NH4HS, and that's the solid that they're asking me about here, in equilibrium with my H2S and my NH3. I know that now initially I've got this pressure of 0.5 for each of my gases here. I know that they're both going to decrease by an X here. Why are they decreasing? Well, I'm starting with the reactants this time and figuring out how much product is being produced here. So they're going to react together and decrease in concentration. And I know that at equilibrium, they should have this concentration of 0.33 atmospheres. I'm sorry, this pressure of 0.33 atmospheres. Again, we calculated that in part A here. So I'm trying to figure out what this X is, and this X will tell me how much of my substance is reacted here. So I know that 0.5 minus X is going to be equal to 0.33. That tells me that X, or my change, is 0.17 atmospheres. That's how much was reacted here. Now everything's in a 1-to-1 stoichiometric ratio here. That means I reacted the same amount of H2S as I did NH3. So I can do a PIV here, PV equals nRT, to figure out this pressure, this 0.17 atmospheres that reacted, how many moles is that? Once I figure out how many moles that is, I can get that to moles of my solid. Remember, my solid doesn't have a pressure. So I didn't react with 0.17 atmospheres of my gases and make 0.17 atmospheres of my solid. I need to calculate how many moles of my solid I made. So we plug this into PV equals nRT. My pressure that was reacted was this 0.17 atmospheres. The volume they give me is a 1 liter container. I'm trying to calculate the number of moles that reacted, so I'll keep that as N. Okay, my R value, I'm using atmospheres here. Remember, this is on our reference table for us. That's 0.08206. And the temperature, it tells me, is at 298 Kelvin. So I plug all this in. I solve for my N, or my number of moles, and that should come out to 0.00695. Okay, so that's the moles of H2S, or NH3, that reacted. Since it's a 1-to-1 stoichiometric ratio between H2S and NH4HS and NH3 and NH4HS, the same number of moles will be produced for my solid here. So I'll have 0.00695 moles of my solid, which was this NH4HS, being produced. Okay, moving on to the next question here. Okay, in the next question, first thing they want me to do is again write that Kp value here. So remember, that's going to be concentration, or pressure of the products raised to their stoichiometric coefficients over the pressure of the reactants raised to their stoichiometric coefficients. So it's going to be the pressure of NH3, and that's going to be squared, and then over the pressure of N2 raised to the first power times the pressure of H2 raised to the third power here. Okay, then in part B, they give me these concentrations, and these are the initial concentrations under these initial conditions. So I can calculate Q here. Remember, Q is going to have the same setup as K, but it's at any point in the reaction. It's not just when these substances are at equilibrium. So to calculate the Q here, I'm going to plug these pressures into my K expression, knowing that this is not at equilibrium. So I'm going to take my pressure of NH3, which is 0.224, and that gets squared. over my pressure of N2, which is 0.411, times my pressure of H2, which is 0.903, and that gets cubed. And I plug that into my calculator, and I should get a Q of 0.166 here. Okay, now I'm going to compare in part 2 that Q to my Kp value. So I see that Kp is 3.1 times 10 to the minus 4. The Q that I just calculated was 0.166, so that tells me that Q is larger. Oh, sorry about that. Q is larger than K. Remember, if Q is larger than K, that means we have too much of my products and not enough of my reactants. I need to get my numerator to be smaller and my denominator to be larger. So my reaction will proceed in the direction of the reverse direction here. So reaction will proceed in the reverse direction. And again, why is it proceeding in the reverse direction? Because we need to use up some of our products and we need to make more reactants here. The numerator's too large, denominator too small, and that's giving me a very large Q value here. If I want Q equal to K, which is when we get to equilibrium, Q is equal to K, the reaction has to proceed in reverse here. Okay, question C. This was an old AP question. This was actually from 2004, and they used to hold you responsible for converting between KC and KP. They don't do that anymore. So we're going to skip that, and if you didn't understand that problem, I'm sorry about that. But question D, we should have been able to do here. So we have our reaction here and a KP value for this reaction. They're asking me to alter this reaction, and that alters my K value. So if I look at part 1 here, it's the same reaction, but in reverse. If I reverse a reaction, remember to get the K, I'll take 1 over the K value here, which would be 1 over 8.3 times 10 to the minus 3. And that'll give me a K value of 120. Now looking at this next part, I'm going to be using both this reaction here listed under D and this reaction here listed all the way at the top, the first reaction that we are working with. And it's like I'm looking at a reaction mechanism here. So I'm trying to get N2 and 3H2 to be on the reactant side, which they are in my first equation here. So I'm going to leave that reaction alone. This reaction here, I need NH4HS on my product side, but I need 2 of them. So I need to multiply this whole reaction by 2. And when I do that, this K value is raised to the power of 2. Then if I add these 2 equations together, well, my 2 NH3s from this reaction and the top reaction end up canceling. And if I look at what's left, well, it's exactly what I need for this reaction for part 2. So to calculate my K for this equation, it's going to be the K from the first reaction that I didn't alter times this second K value, I'm going to call that K2, and this value was squared because I multiplied that whole reaction by 2. So I'll end up taking, again, that K1 value was 3.1 times 10 to the negative 4, and that's unaltered because I didn't alter that reaction, and then times the second K value was 8.3 times 10 to the minus 3, and that's squared. And when I multiply those together, I should get a value of 2.1 times 10 to the minus 8. Remember, these K values are unitless, so that's my final answer here. Okay, moving on to the next question. Okay, this was a throwback with the mole fraction. Remember, the mole fraction is going to be the moles of whatever substance I'm talking about over the total moles in the mixture. I can assume that I have 1 liter here since I'm not given a volume here, but the mole fraction will come out the same no matter what the volume is if I'm given the molarities. So they're asking me about CO, and I see right here that CO is 0.55 moles per liter. So to calculate the mole fraction, I know that there'll be 0.55 moles of CO. Then I add up my total moles here. So my total moles is 0.2 from my H2 plus